So we already know that the force is on a particle in a field is Q V cross B, where B, remember, is the magnetic field and V is the velocity of our particle. Q is the charge. This is a vector quantity, vector, vector, vector. What we can do to kind of work to more advanced problems is take a charge flow, i.e. a current. So if a current is running through the wire, what really is a current? Remember, a current is a bunch of particles that are moving through a wire. And we define current as the motion of positive charge, the rate of change, dq dt. And we know that it's actually the motion of negative charges, but we just reverse that direction. And so I is dq dt. You can also rewrite this idea of velocity. Right? Velocity, we know for a long time, is dx dt. And so we can replace our terms in our force equation with the ones that we've written out here. So we can say force is, instead of dq, we can have I dt. And then instead of v, we can have dx dt. Okay? And then we can cross that with b. Now, as we begin to simplify, you should notice that the dt terms will cancel out, and you'll have I dx cross b. We'll, of course, need to integrate this part of the equation in order to come up with the full force effect. Right? If you just have I dx, then that won't be the complete part. That will just be the force on a small segment. So to get the total force, we'll need the integral of that. Right? So I guess this should be a df. All right, nice. And if you just evaluate this from 0 to L and dx is just a specific length, then you have your baseline formula, which I used, for example, in like AP2, of IL cross B, where IL is a vector quantity and B is a quantity. And that's going to give us our force. Very good. Let's try to apply this on some other questions to relate this back. And when you use your right hand rule, your force is still going to be your thumb. This IL, which replaces the QV idea, charge flow, is going to be your pointer finger. And then your B is going to be your field. So perhaps you would set this problem up like this. Okay, so here you see that the QV is going to be replaced with, look at the quantity now, IL, and that points up, same direction as the current. The B is a symbol and points in, and F is the force from our thumb, like that. Okay, so to remind you that these problems can get more advanced, although we often don't deal with them, we can write a current density function as you see this letter J. So J is current density, dI, dA, and most of the time this is just a uniform current throughout the wire and we don't worry about it. But if we have some sort of function of I that changes throughout our length of our wire in some way, we just should be aware of that if the area of our wire is changing. That has never come up for us before, but worth saying for when you go to more advanced physics. Okay, help you set the scene. So here is a wire that carries a 15-meter current from west to east in a region between the poles of a large electromagnet. And in this region, there's a horizontal magnetic field northeast. Horizontal. So in our picture that I drew over here from a side perspective, horizontal is going to look something like this. So we can put the bar in our picture. Whoop, there we go. And we can put the magnetic field of 1.2 Tesla in our picture as well. Notice that the magnetic field points north and east. So I suggest we break it up into components. So we'll say that some of our B is east and some of it is north. But when transposing north into our picture, let's put north as into the page, and we'll use this nice symbol for that. So we can just use our standard components, B like cosine 45 and B sine 45, where B will be 1.2 Tesla. Okie dokie. Let's try that out. All right, here's what our B looks like. So when you begin to set up your cross product, we realize that only part of this B is going to affect the value of the cross product. We have force is IL cross B. So you'll notice the B to the east can't be crossed with the IL to the east, right? So we're only going to use B north. We're going to get rid of this cross product. We're going to say sine 90. And then our IL will be to the east. So let's go ahead and fill in some numbers. So the force here is going to be our current, 50, times the length of the wire. It says a 1 meter section. And then sine 90 is just 1. The B that we're using is going to be B sine 45. Okie dokie, nice job. And then go ahead and set your right hand up. And to discover the direction of that force. And so on our beam, you have your, let's see, you have your B's pointed in. Those are your fingers. Your pointer finger points to the right. And then you find your thumb pointing up. So this is the force from the magnetic field. Now you should realize there's also a force down because this is a wire, right? mg. So this is something that we call magnetic levitation, where the magnetic force can balance the gravitational force, right? All right, now it says that what mass of the rod can be supported, assuming equilibrium. So let's take this value of force, which is up directed, and we'll set it equal to the down directed force, right? mg, or we know what g is, and we can solve for m. Okay, so this here, by the way, taking the back step, was sum of the forces equals 0, because we are in equilibrium. Now it says, while keeping the rod horizontal, how can we maximize the force? Well, let's see, maybe we could take our rod like this. We can make our cross product, instead of only using a component, we can use all of it. So what would that look like? Let's see, let's orient it like this. Oh no, completely opposite that. There we go. So our I and our B's are perpendicular to each other. Good job.